Let's talk about relative velocity. What does that mean? Well, we talked about it a little bit, but this is when objects are moving with a medium that might be moving with respect to an observer or staying still with respect to an observer. So we've actually already talked about a situation like this, and that is if you're walking on a train at 2 meters per second, then are you going 2 meters per second, or are you going 2 meters per second plus the train's velocity, which in this case is 9 meters per second? And the answer really is, well, it depends on where you're looking from, right? If you're somebody who's on the train, who's sitting still on the train, then the person walking on the train is walking 2 meters per second. If you're walking on the ground, or not walking on the ground, if you are on the ground observing this person walking on the train, then they're going 11 meters per second. So that's what relative velocity means. It means relative to where your perspective is, what's happening. Okay? So another example of this is when an airplane encounters wind, because of course how the airplane is moving relative to the ground might be different than what the speedometer reads for the airplane. So, for example, say we had plane velocity of 100 kilometers per hour south, and then the wind was also blowing south at 25 kilometers per hour. Well, that's going to help the plane now. And so the plane's speedometer tells it's going 100 kilometers per hour. It's actually going 125 because the wind is also pushing it, right? But this can happen in the opposite direction, where if the plane's going 100 kilometers per hour south, but there's a north wind of 25 kilometers per hour, then that's going to cancel out and it's actually going to be going 75 kilometers per hour. So that's another example of relative velocity. Yet another example that we're going to go over is a boat on a river, and this one we're going to see a lot when there's a current. So, the boat tries to cross the river, there's a current, so it's going to go off at an angle. So an observer on land is going to see the boat moving at a different velocity than the people in the boat are going to see. Okay? Because again, if somebody on the boat is rowing to the right, but the current's actually going to the south, then the boat's really going to take a trajectory like that. But if you're on the boat, you're always going to be seeing yourself directly across from the other shore, right? So it's going to be very, very different, where on the boat, you just see this is your velocity, the velocity of the boat relative to the water. But if you're standing on the shore, you're going to be seeing the boat do this. It has a velocity of the boat plus the velocity of the current, but of course, since that's in a different direction, we kind of have to make a vector diagram like this, okay? And so that's what I'm talking about when I talk about relative velocity. You have to kind of look at what your frame of reference is. Okay, so again, a lot of the time we're going to be looking relative to the ground and saying what's actually happening when we have a plane in wind, or we have a boat, but it's going on a river with current. Okay? So a few tips to solving these kind of problems. Remember, your resultant vector is relative to the ground. Okay? So always picture yourself as the observer, not the person on the boat, not the person on the plane, not the person in the car or the train. You are an observer on the ground. Always adding vectors tip to tail in order to get that resultant vector. Okay, so if I know that somebody is heading north across the river, then I'm going to draw a vector north. If I know the current is going to the east, I'm going to draw a vector east, and then of course adding my final vector in, the resultant vector from tip to tail. Okay, and then another reminder is that the resultant vector is not always the hypotenuse, and I'm going to show you an example like that in a minute, so make sure you're paying attention to that. Okay, so we have a boat heading north with a speed in still water of 6 meters per second. Okay, so that's the velocity of the boat that it just gave us. So I'm going to call that V with a little B down there, so I know it's the velocity of the boat. The current is 4 meters per second east. So I'm going to call that VC, the velocity of the current. And I want to determine the velocity of the boat relative to the shore. Okay, and I will call that VS, velocity relative to the shore. So again, let's draw a vector diagram. So we know its speed in still water is 6 meters per second, and that's heading north. So I'm going to draw that first. Okay, so there we go. So we know that's the velocity of the boat is going north. Now, the current is 4 meters per second east. So I'm going to draw a vector going east. Okay, a little bit shorter than the one before. So there's the velocity of the current. And so I need to determine the velocity of the boat relative to the shore. So again, you're on the shore. So here's the shore. You're right here. Woohoo! And you're saying, okay, what does it look like the boat is doing if I'm looking at it in the shore? If it's heading north, but then the current is east, it's going to look like it's going northeast like that. So there's the velocity relative to the shore. Okay, so remember, ask for velocity, so that's the magnitude, but also velocity is a vector, so we need the angle as well. So I'm going to find both of those. Okay, so I know velocity relative to the shore. In this case, it is the hypotenuse, so I'm just going to use Pythagoras where I add the other two together. Okay. And we get a velocity relative to the shore of 7.2 meters per second. Lovely. So that's the speed that the boat is going relative to the shore, but I need the velocity, which means I also need a direction here. And since it's going off at an angle, I need to find that angle. So the tan of the angle should be opposite, which is the velocity of the current, divided by adjacent, which is the velocity of the boat. And my angle, I get the inverse tan of VC over VB. And that should give me the angle that it's going. And then you just have to find the directional coordinates. Okay? So that gives me an angle of 34 degrees. Okay? And then I have to figure out what direction is this. So, again, start at the first one that you drew. And if we start north, and then go east of that, we have 34 degrees. So this is east of north, right? Because you start from the north and you go 34 degrees east of it. There we go, east of north. And there's my velocity relative to the shore. So that's what you on the shore will see. You'll be like, oh, it actually looks like they're going 7.2 meters per second, but at an angle of 34 degrees east of north. Okay, next one. So here we have a boat that wants to land. What does that mean? At a dock located due north. Okay, so it wants to go due north, but there's a current. So the boat can travel 6 meters per second, but now we know that there's a current 4 meters per second east. Okay, so what the heck is going on? So it seems a lot like that one. It's like, okay, aren't we just doing the same thing? No, we're not. So same river. The current is definitely going to the east, but if the boat starts here, it wants to go due north, okay? This is what the boat wants to do. So that's actually what the velocity relative to the shore should be, because the boat wants to do that. It wants to go due north like that. So what should the boat do to offset the current that's going to the east? It should probably go northwest in some direction, shouldn't it? Because it wants to offset, this velocity of the current going to the east. So how the heck does it do that? How about doing that? Yeah? So what if my boat actually heads in that direction? In that kind of northwest direction. And then the current pushes it to the east, and then look at that, it goes straight across. So anytime you see this wants to land, that's when you know that it's actually going to offset how it's going so it can go straight, and what we're looking for is not the hypotenuse. Okay, so it says in which direction should the boat head, so we're finding the angle first. Okay, So in this case, I have the velocity of the current and the velocity of the boat. I do not have opposite and adjacent. I have opposite and hypotenuse. I don't have the adjacent side yet. That's velocity of the relative to the shore. I don't have that. So right now I have opposite, that's the velocity of the current, over hypotenuse, that's the velocity of the boat. So I need to use sine, okay, to get this. So that should be the velocity of the current over the velocity of the boat. So my angle, I should be able to use the inverse sine here of 4/6. And what do I get? I get 42 degrees. 42 degrees what of what? Well, again, look at that. We start north and we go west of it. So that is west of north. Okay. Oopsie. I didn't mean to do that. There we go. So there's my angle. And now part B says, what's the velocity of the boat relative to the shore? So since I have already found, or actually, no, the velocity of the boat relative to the shore, the direction will just be north. So we just need to say that it's going north. So in this case, I'm not going to add when I get to Pythagoras, am I? No, I need to take the hypotenuse, square it, and then subtract the shorter side and square it, right? Because that's how Pythagoras works, which I'm not going to go over in detail, I'm sorry. Because I'm pretty sure you guys know how to use Pythagoras at this point. Okay, so when we do that, we get a lovely value of 4.5 meters per second. Okay, and of course that is going north because they wanted to go due north, so we made them go due north. And there we go. Beautiful. Okay, so that is definitely a situation that mixes so many people up. So anytime you see this, the wants to land, they want to, okay, well then they're going to have to do some planning before. Okay, if it's just somebody that like heads off in a certain direction, well they don't care, obviously. They're just doing anything willy-nilly that they want. But if somebody wants to do something and has like thoughts and plans beforehand, they're going to plan out, they're going to do their calculations. Okay? So in these boat crossing kind of things, if you want to solve for distance or time, right, because we have velocity in a lot of these, then we have to use the velocity vector in the parallel direction. So if I want the distance across the river, then I need to use the velocity that's parallel to whatever across the river is, right, if it's directly across. So what the heck does that mean? If I want to know, again, across the river, this time the river is kind of going east-west, so that's this. And so it looks horizontal here, so I need to use the horizontal velocity that I have if I want to figure out that distance, okay? If I want to figure out how far downstream they planted or landed, that's a vertical direction, so I need to use the vertical velocity, okay? So always make sure you use the thing in the parallel direction if we want to solve for distance or time, okay? So for example, a river is 60 meters wide. We would like to determine the time it takes to cross the river. Okay, so it's 60 meters wide, and we have the horizontal velocity. So I'm going to use all my horizontal stuff, so all my stuff in the x direction, because I have the velocity and I have the distance. So I'm going to find time that way, okay? And I get a time of 15 seconds, okay? So there we go. There's the time it takes to cross the river. And again, as long as I use the parallel directions, then you get the correct answer. How far downstream does the boat land if the current is 3 meters per second? So here, my current is 3 meters per second, so I want to know how far down here is it landing, okay? So if I want that, again, it's a constant velocity. The current's going constant, the speed of the boat is constant, so I just use v equals d over t. So this distance, this is going to be the y direction in this one. is equal to velocity times time. Yay, so that's just 3.0 meters per second times that 15 seconds. Because just like in what we were just covering, if I have the time in the x direction, that's the same as the time in the y direction. Okay, that one doesn't change. Because that really is just the time to cross the river. So there we go. So that one's 45 meters downstream if it's going 3 meters per second. Okay, so they're going to land down here at 45 meters from where they started heading. How far downstream does the boat land if the current is 5 meters per second? Well, that doesn't change much, right? So I still have how long it takes because I used my horizontal things to find that, and the horizontal velocity and distance is not changing. So I can still just use distance is equal to velocity times time. But now my velocity is 5 meters per second. Okay? And that gets us 75 meters. So remember, as long as you're using the things in their parallel directions, then you should be just fine. Okay, let's just do a few more things. I just want to get your head wrapped around, this resultant velocity and relative velocity. Okay, so I want to know, look at these 4 diagrams and tell me which you think, in which case does the plane travel the fastest when you're looking at it from the ground? And which time does it look like it's going the slowest when you look at it from the ground? Okay, so let's figure out how we're going to do this. A, the wind is just pointing it to the right while it's going north, so not much is happening there. Let's look at B. So what's happening here is the wind is pointing it to the right, but it's also pointing it along its path. So therefore, it's actually helping it a little bit, helping it go faster, right? So that could be the fastest along the round, but let's see. Part C, again, this vector, it's pointing it a bit to the right, but it's also pointing backwards. All right, so what's that mean? That means that it's going against the airplane. So that's actually going to slow the airplane down. So that's probably our answer for the slowest along the ground. And then for part D, again, wind is pushing it a little bit to the left, but it's pushing it also forwards along the plane's path, and that's good. And that looks like a bigger vector than this one right here. So I'm actually going to say plane D is going to be going the fastest. Okay. And I'm going to go ahead and say C is going to be going the slowest because it's the only one that has wind that's going against the plane. Okay? So again, please keep all that in mind when you're looking at relative velocity. One more. Which boat takes the shortest path along the river? Okay? So I want to turn these into vectors. So I have if you don't see, we have like the directions that it's heading and then the current, okay? So in A, the velocity of the boat is going this way and the current is going down. So what is the velocity relative to the shore in this case? Looks like it's pretty much going right across the river, doesn't it? So that's the total velocity. So to me, it looks like that's probably going to be the shortest path. But let's double check. With B, the boat is heading this way. It's the velocity of the boat. The current is still heading south. But again, I'm going to draw the tip to tail version. So there's the velocity of the current. So it looks like my boat relative to the shore is going along the hypotenuse. Okay. And then finally, we have part C, where our boat is headed off kind of in this direction, right? And then the current is going this direction. So this is actually taking a much longer path, isn't it? Okay, because there's my velocity of my boat, there's velocity the velocity of the current. So the velocity relative to the shore is much bigger. So the shortest path is definitely going to be A. Okay, because it's traveling straight across the river. Okay, which boat reaches the opposite shore first. Okay, don't get too ahead of yourself. Opposite shore first. So to reach the opposite shore, that's like a horizontal distance, right? Saying which one's going to cover the horizontal distance the fastest. So I need to look at my vectors in the horizontal distance, or in the horizontal direction. So this first one for A, it's not going to go as fast because remember when the boat could go 6 and the velocity of the current, we had to subtract those. So this guy, if the velocity of the boat is going right across at 6, then that's pretty good. And then here the velocity of the boat isn't even going right across. So the answer to this one is actually B, because it has the highest horizontal velocity, and that's why. So that one's a little bit tougher. Alrighty, and finally, which boat has the fastest speed? So look at the fastest velocity relative to the shore, i.e. the biggest arrow. That's this one over down here at C. It's the biggest arrow. So it has the greatest velocity due to that vector addition. Okay? So C is actually going the fastest because it's the biggest vector. All right, so that's it for relative velocity. Go work on the questions on page 120 to 123, numbers 1 to 7, and good luck with those.